Hello SIGGRAPH, hello everyone. Today I'm here to present our work, Virtualized 3D Gaussians, flexible cluster-based level of detail system for real-time rendering of composed scenes. This is a joint work with Linning Xu, Li Hanjiang, Dahua Lin, and Bo Dai. I will first introduce the background. 3D Gaussian splatting is a fast way to reconstruct digital 3D assets from multi-view images. Each asset contains many explicit 3D Gaussian primitives. With the GPU rasterizer, rendering each single asset is super fast, far beyond real-time requirements. It is natural to compose 3D scenes with these reconstructed detailed assets. For example, the composed scene do not see, forest, crowd, and temples, each containing 100 millions of 3D Gaussians. However, though rendering each asset is fast, the rendering speed of composed scene is low. The target of our work is to achieve real-time rendering of composed scenes. We observe that the main issue is the rendering process of 3D lacks a level of detail mechanism. It is unreasonable to rasterize 300,000 of 3D Gaussians at both high and low resolutions. We tend to adopt level of detail for 3D Gaussians. We found that Nanite virtualized geometry in Unreal Engine 5 solved the same problem. Nanite is the LOD system for detailed static mesh, rendering pixel scale detail and high object counts. 3D Gaussians are explicit 3D primitives with spatial extent, similar with triangles, so we try implementing Nanite system on massive 3D Gaussians in composed scenes. Inspired by Nanite, we propose virtualized 3D Gaussians. Instead of directly rasterize all 3D Gaussians, we design the offline build stage and the online selection stage to select less 3D Gaussians to rasterize. During the offline build stage, we post-process each reconstructed 3D GS asset in the composed scene, generating clusters at different levels of detail. During the online selection stage, based on camera distance and resolution, we select clusters at appropriate levels of detail to render the final image. Core designs in these two stages will be introduced later. With this LOD system, we can achieve real-time rendering of complex composed scenes. For example, we selectively render around 10% of 3D Gaussians when the camera is far, achieving around 7 times the acceleration. When the camera gets closer, clusters with more details are selected for better visual quality. Next, I want to introduce the offline build stage. We use the cluster as the basic unit in our LOD system, each cluster containing adjacent 3D Gaussians in 3D space. Compared with single 3D Gaussian, a cluster is more meaningful and is easier to optimize. We first split the 3D Gaussians in 3D GS assets into the finest cluster C0, and iteratively create cluster layers. The core of the offline build stage is the simplification process, how to simplify two clusters into one. A naive solution is sampling half of 3D Gaussians, however the quality is unsatisfactory. Thanks to the differentiable feature of 3D Gaussians, we optimize the initial half of 3D Gaussians to distill the appearance of the original 3D Gaussians, using random cameras positioned around them to render images and optimizing the properties of the newly created 3D Gaussians. It is good that the proposed local splatting method helps maintain local appearances between adjacent layers. Here we show the effectiveness of local splatting. Longer optimization maintains the appearance of original assets better. Then the online selection stage. The goal of the online selection stage is to select clusters at appropriate levels of detail. But first, we need to define and measure the level of detail. Simply, we define the level of detail at the area of the projected 2D footprint of the bounding sphere. If the footprint is smaller, the cluster group is more detailed. During online rendering, each cluster has its own footprint. A given tolerance forms a cut in the tree and selects clusters at appropriate levels of detail. A smaller tolerance selects more detailed 3D Gaussians, while a larger tolerance selects less 3D Gaussians and renders faster. Okay, some results. Our method can accelerate the rendering, especially when the camera is far. When camera gets closer, the detailed objects appear continuously. This can facilitate downstream interactive applications that compose extensive 3D JS assets for consistent rendering performance. Except for the rendering acceleration, another good aspect of our method is the introduction of anti-aliasing. Vanilla 3D.js causes aliasing artifacts when the sampling rate is much lower than that of the assets. Our method instead matches the frequency of the asset with the sampling frequency, mitigating the aliasing artifacts. Here we use the 4K super sample anti-aliasing for comparison. You can say that our method generates more comfortable renders. And we compare our system with two baselines. All selects around 20% of 3D Gaussians. The top row shows the clipping strategy from the gsplat library. Unlike our method that always selects full parts of an object, it causes holes and introduces more error. The bottom row shows the related work hierarchical 3D Gaussians. After some modification, it can be applied on acceleration of composed scenes. However, our method performs better than their method by adopting the cluster instead of single 3D Gaussians as a basic unit. And finally, the conclusion. To conclude, we propose virtualized 3D Gaussians, a post-processing cluster-based level of detail system for rendering approximately 100 million 3D Gaussians in digital worlds in real time, with a build stage constructing hierarchical clusters and a selection stage that filters necessary clusters. Finally, our work has limitations. Though we send less 3D Gaussians into the rasterizer to render, we use twice the storage to save the bundle. Currently, our work is not fully virtualized, lacking a streaming module. Composed scenes used for evaluation are simple and far from digital scenes in production. We leave addressing these limitations and exploring possible improvements to future work. This is our project Virtualized 3D Gaussians. For more results, technical details, and the code, please refer to our project page. Thank you.